Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Mathematical Optimization Models, Duality Gap Problems. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. In mathematical optimization, the duality gap is the difference between the value of the objective function of a primal problem, and the value of its corresponding dual problem. Understanding the duality gap. Dual variables do not recover all costs, the unrecovered cost is equal to the magnitude of the duality gap. This will imply losses for market agents. Some applications related to the topic. Price overestimation. In combinatorial auctions with strong complementarities, dual prices often overestimate the true value of items due to the duality gap. Algorithm performance. Optimization techniques such as Lagrangian relaxation are used to address these gaps in large-scale problems, such as unit engagement in energy auctions, where the duality gap serves as a measure of the quality of the solution. Duality theory is a powerful and widely used tool in applied mathematics for several reasons. The dual problem is always convex, even if the primal is not. The number of variables in the dual is equal to the number of constraints in the primal, which is often less than the number of variables in the primal problem, and the maximum value reached by the dual problem is often equal to the minimum of the primal. In the mathematical theory of optimization, duality or duality principle is the principle that states that optimization problems can be seen from two perspectives, the primal problem or the dual problem. If the primal is a minimization problem, then the dual is a maximization problem, and vice versa. Any feasible solution to the primal problem, minimization, is at least as great as any feasible solution to the dual problem, maximization. Thus, the primal solution is an upper limit of the dual solution, and the dual solution is a lower limit of the primary solution. This fact is called weak duality. The duality gap is the difference between the primal solution and the dual solution. If D is the optimal dual value and P is the optimal primal value, then the duality gap is equal to P, D. For minimization issues, this value is always greater than or equal to 0. If the duality gap is 0, a strong duality is said to remain, otherwise, the gap is strictly positive, and the weak duality remains. Computational duality theory. In computational optimization, another duality gap is often reported, which is the difference in value between any dual solution and the value of a feasible but suboptimal solution in any one iteration for the primary problem. This gap quantifies the discrepancy between the value of a feasible but suboptimal iteration for the primal problem and the value of the dual problem. The value of the dual problem is equal to the value of the convex relaxation of the primal problem. Convex relaxation is the problem that arises when replacing a non-convex feasible set with a non-convex function with its convex closure, i.e., the function of the epigraph that is the closed convex envelope of the original primal objective function. In the calculation of prices in auctions with complex rules using optimization models, when the problem is convex there is no duality gap, but this is not the case in the presence of non-convexities. More precisely, in areas where the problem is not convex, small changes in the price signal cause large leaps in the solution of the dual problem. As a result, the primal problem satisfies exactly all the constraints, but it differs easily from the solution of the dual problem. This is the case with mixed linear programming models, which are not convex. In auction pricing with complex rules using optimization models, when the problem is convex there is no duality gap, such as linear programming, but this does not occur in the presence of non-convexities. More precisely, in areas where the problem is not convex, small changes in the price signal cause large leaps in the solution of the dual problem, making it impossible to satisfy the loose equation, the supply-demand equilibrium. As a result, the solution of the primal problem satisfies exactly all the constraints but differs easily from the solution of the dual problem. This is the case with mixed linear programming models, which are not convex. The marginal cost problem. When integer/binary variables exist in the context of short-run auctions, energy refers to the short-run competitive equilibrium. Agents should have no reason to change the allocation assigned by the auctioneer, which implies the recovery of operational costs for all agents participating in the auction. However, this is not always enough to choose between traditional pricing schemes, so it is necessary to look for alternative or complementary schemes. The figure shows the classical geometric illustration of Lagrangian dualization, which contains optimal primal value, optimal dual value, duality gap, and best supporting hyperplane. The points in the set, indicated by the gray area, denote an optimal value. This case is of a zero duality gap. The points in the gray set indicated that the case corresponds to a positive duality gap. The figure illustrates the dissection of fx and θ mu in a non-optimal feasible primal solution, epsilon, and a non-optimal dual solution, delta. The epsilon and delta functions are introduced, and the figure shows their optimal values. Since mu is not optimal, the line θ equal to z plus mu multiplied by ni supports the set of non-optimal solutions, color white, at only one point x, which may be feasible or infeasible. The case corresponds to a duality gap. Electricity markets optimization. Case, duality gap. The use of optimization models in a market environment continues to face several challenges. This section discusses the duality gap problem in simple auction optimization models. The publications of Madrigal and Quintana have been taken as a reference. Degeneracy and duality gap can exist even in very simple optimization-based electricity auctions, and they have important effects on the meaning and usefulness of dual variables in setting the market price. An optimization model of a simple auction is described, in which participants only present the amount of energy offered and its unit price. Using duality theory, it is shown that Lagrange multipliers can be used to set the market price and that, in the absence of degeneracy, they reflect marginal prices and are equivalent to a percentage price auction. The conditions under which multiple primal solutions exist for this model are described. For a bid auction in which an efficient initial cost and a variable cost are presented, it is concluded that, in the absence of the duality gap, the Lagrange multipliers used as market prices lead to the recovery of all costs. When a duality gap exists, the dual variables do not recover all the costs. Moreover, the unrecovered cost is equal to the magnitude of the duality gap. The article describes the conditions under which certain types of multiple primal solutions can be identified. Several illustrative examples of auctions are presented throughout the article. The marginal cost problem, when there are discrete variables in the context of short-term auctions, such as energy, refers to the short-term competitive equilibrium. Agents should have no reason to change the allocation assigned by the auctioneer, which means that agents should recover operational costs in the auction. However, this is not always enough to choose between traditional pricing schemes, so it is necessary to look for alternative or complementary schemes. The marginal cost problem, when there are discrete variables in the context of short-term auctions, such as energy, refers to the short-term competitive equilibrium. Agents should have no reason to change the allocation assigned by the auctioneer, which means that agents should recover operational costs in the auction. However, this is not always enough to choose between traditional pricing schemes, so it is necessary to look for alternative or complementary schemes. Madrigal presents an example of a plant dispatch that contains the data of 5 bidders with linear and constant startup costs. Although the model is simple, the results help to understand the conditions under which optimization models can be used and the information they provide to conduct electricity auctions. The operating cost of a plant is made up of an initial startup cost plus a linear operating cost. The model includes a binary variable equal to 1 if the plant is in operation and 0 otherwise. The operating power of the plant is a continuous variable. The MPA optimization problem for solving auctions is called MPA. The introduction of binary variables makes MPA a non-convex optimization problem, and therefore the duality gap may exist in some situations. This type of bid format, while simple, is designed to determine a market price for energy, and all participants will receive that price for the energy they sell to the market. In theory, the price should be such that it recovers the costs of the participants. If assuming that demand is inelastic, the cheapest offers will be selected to meet demand. The market price is usually determined as the purchase price of the last supply used to meet demand, This pricing scheme is known as marginalist. The dual function is piecewise concave. It is made up of line segments with points of rupture, or change of slope. Since the primal problem is feasible and bounded, then there is a primal and dual optimal solution, and they have the same objective value. The dual optimum occurs at the maximum of the dual function. To learn auction behavior, the cost minimization auction is solved for the following demand levels: 52, 110, 130, 190 and 210 megawatts. Madrigal analyzes the case of 5 bidders with the following parameters. Alpha equals startup cost, beta equals to operational cost, and maximum power. The figure shows the results of the 3 levels of demand that can be visualized in the supply-demand curve. Each of the cases represents one of the possible situations for auctions. In the first case, demand equal to 70, there is a unique solution to both the primal and dual problems. The Lagrange multiplier can be used to clear the market. In the second case, the demand is equal to 100, the solution is primal degenerate, and the optimal Lagrange multiplier has multiple values in the range of 10 to 20, and it would be selected as the market price. However, in this case, this value does not reflect a marginal price since the actual marginal price is 20, which is the cost of supplying a sufficiently small increase in demand. In the third case, demand equal 250, there are 50 megawatts that can be equally allocated between bidders 4 and 5. The way in which the power is assigned must be established by the market rules. The cost minimization auction is solved for the following demand levels: 52, 110, 130, 190 and 210 megawatts. The complete list of dispatch possibilities can confirm that the solutions presented are optimal in all demand cases. The table below summarizes the costs, revenues, and profits for each of the solutions when the price is equal to the smallest optimal dual variable, when there is a balance. In equilibrium, this rule leads to positive profits for all bidders and is analogous to a first price auction in which the last bidder makes a profit equal to 0. In imbalance, some of the bidders do not recover the cost, and the total unrecovered cost is equal to the duality gap. Corner indicates the duality gap in the instances analyzed. Pi corresponds to the dual variable for each case of demand and each bidder. The total supply function is shown in the figure, for the 5 demand scenarios. Qualitatively, the table presents the results for the 5 demand scenarios. The solution is analyzed mathematically. 52. There are infinite optimal solutions. Since 30 megawatts can be supplied in an infinite number of ways by suppliers 4 and 5, assigning a power equal to x to supplier 4 and 30 minus x to 5, for values between 10 and 20, the same objective function value, $2,140, is produced. There is no market equilibrium, and the optimal dual variable is unique. 110. There are 2 optimal solutions. There is no market equilibrium, and the optimal dual variable is unique. 130. There are multiple optimal solutions, only 2 of them are shown. The first solution contains offers 4 and 5, and the second contains offer 3. There is no market equilibrium, and the optimal dual variable is unique. 190. The primal solution is unique, but there are several equilibrium prices in the range between 25.78 and 26.75. 210. There is a single equilibrium price and 2 optimal primal solutions. The costs, revenues and benefits of each of the solutions, when the price is equal to the smallest optimal dual variable, and there is an equilibrium in the market, this pricing generates positive benefits for all bidders. This rule is analogous to a first price auction in the sense that when equilibrium exists, the last bidder, marginal bidder, makes a profit equal to 0. For cases in disequilibrium, some of the bidders do not recover the cost. In all these cases the total cost not recovered is equal to the magnitude of the duality gap. Qualitatively, the table presents the results of the 5 demand scenarios, for bidders. It is analyzed what they think after the auction. 52, at a price of $15.80/MWh, Bidder 2 wants to increase its production to 50 megawatts to maximize its profits. 110 cents price is between 25.78 and 26.75. Bidders 4 and 5 want to reduce their production and operate at zero profit. 130. All the possible optimal solutions to supply 30 megawatts between tenders 4 and 5 generate the same unrecovered cost of $46,667. At the price of $25.78/MW, bidders 4 and 5 wish to reduce their production to zero to avoid negative profits. In the second case, bidder 3 would like to increase to maximum production to maximize profits. 190. There is equilibrium with an optimal program. The bidders agree with the allocation made. 210. There is an equilibrium between two optimal programs, both solutions offer the same benefit. Although bidders 4 and 5 are not scheduled, they don't care about the deadline that is finally implemented. The 110 and 130 megawatt scenarios show that some bidders want to withdraw from the auction, but others want to increase their bid. In the other scenarios, the situation is more attractive. There are bidders who want to offer more or who do not care what happens. Electricity markets optimization. Case, unit commitment. The article discusses the problem of defining marginal costs when integer variables are present, in the context of short-term energy auctions. Most of the proposals for price calculation relate to the short-term competitive equilibrium, in which generators should not be willing to change the dispatch allocated by the auctioneer, which implies the recovery of operating costs for all generators in the auction. Using this condition, a single solution to the problem of defining prices is obtained, calculated as the shadow prices of the balance equations in a linear version of the unit commitment problem. Compared to other proposals, the results provide a strong motivation for the pricing scheme and a straightforward method for price calculation. It is important to note that not every linearization of the commitment to unity is valid, therefore, conditions are developed for this linear model to provide adequate reversal signals. However, this is not enough to choose between the different pricing systems. It is proposed to include an additional criterion to discriminate between different price systems that should also be signals of generation expansion. This last topic is not covered in this lecture. It is often mentioned, Ferrer in 1993, that the duality gap decreases with the size of the problem, being negligible for large-scale optimizations. This is true in relative terms when considering the total cost of supply. The value of the duality gap for the marginal unit remains unchanged, but, as the system is larger, the number of generators at full load, without the duality gap, increases, and compared to the total cost, the value of the total duality gap is relatively smaller. However, the generator's sources of income in a single price market are not met. The duality gap for the marginal generator remains unchanged and results in an error in price calculation, which in turn is paid to all producers. In a market, the problems linked to the duality gap do not reduce with the size of the problem. The market could be described as a process in which a central problem, the previous day's auction, fixes the price, and each producer solves his own sub-problem to determine his production. In other words, the centralized unit commitment problem is solved by a decomposition technique, which allows for distributed optimization. Each generator decides its own production, and leaves the price as a control variable that creates economic signals to ensure that the generation-demand balance is maintained. This type of decomposition, where a certain constraint is replaced by a price signal, is known as Lagrangian relaxation. The explication of the diagram is top. Example of a unit commitment problem illustrated in the time domain for different types of generators, storage, and demand, which must cope with intertemporal constraints, ramping constraints, contingencies, and forecast errors. Bottom. The same problem conceived as an instantaneous sequence of independent market equilibria between supply and demand, solved every 5 minutes using the substitutable flow raw material paradigm. In the context of thermal unit commitment issues in early 2026, the duality gap remains a critical metric for assessing solution quality, especially when using Lagrangian relaxation. Multiple instance cases for the auction are then analyzed. Production decisions for price equal to the variable cost of the marginal unit, aggregated view. The results shown in the figure present the total cost of production as generation increases. The optimal solution is the point at which generation equals demand. In a context of perfect competition, each generator decides its production by maximizing its revenue from market sales minus its operating cost. Production decisions for price equal to the variable cost of the marginal unit, plant-by-plant view. The decision process of market players is shown in the figure, where the solid lines show their operating costs and the dotted ones represent their market income. Production decisions for price equal to the variable cost of the marginal unit, aggregated view. From this point of view, a straight line with a slope equal to the market price, and tangent to the cost curve, represents the optimal response of the system's generation portfolio at a given price. The figure shows this reasoning: the market price is equal to the pure marginal cost, with the dotted line being the lowest line, and has the same slope than the variable costs of marginal generator. Production decisions for price equal to the average cost of the marginal unit. An alternative candidate for the market price is the average cost of the marginal plant, which should ensure that the price pays for all the operating costs of this generator, and therefore it will be willing to come online. This price is in fact high enough that the marginal generator is willing to produce. However, operating at the partial level, determined by global optimization, does not maximize its benefits. Production decisions for price equal to the average cost at maximum output of the marginal unit. An alternative is to define it as the average cost based on the maximum production of the marginal plant. Under this solution, all units that were not dispatched in the optimal solution are unwilling to produce, and no inframarginal unit has incentives to stop producing. This means that, for all units except the marginal one, this price maintains the global optimum as equilibrium. However, the optimal response of the marginal plant is to stop producing, or to produce at its maximum capacity, since a level of generation other than its maximum production would reduce its revenues, making them lower than their operating costs and, therefore, causing the cessation of production of the plant. If there is no price that supports competitive equilibrium, then the only option for identifying a reasonable pricing mechanism is to move away from the single price scheme and try to find an alternative approach to dealing with pricing. Most of the proposals suggest that generators receive their short-term income from two sources. On the one hand, an energy price, paid uniformly to all the generators that are producing at a certain hour, and calculated as some form of marginal cost. Details vary depending on the solution. On the other hand, a side payment, different for each generator, and often restricted only to a few of them, or even only to the marginal one. Using sideways payments, the average cost solution at the maximum production price described above could be transformed into a short-run competitive equilibrium solution simply by giving the marginal unit an additional payment. This additional revenue would be equal to the portion of its fixed cost corresponding to the capacity it is not actually producing. Therefore, the authors propose to implement the day-ahead market auction as a three-steps procedure. The model includes the side payment optimization. Solve the scalable generators linear problem, SGLP, which is a particular linearization of the unit commitment problem, and obtain hour market prices. Solve the unit commitment problem, UC, which is a standard unit commitment with binary variables, and obtain the quantities that are assigned to each generator in each hour, together with their production costs, and compute a side payment, SP, for one, or a few, near-marginal generators as the difference between its total operational costs and its total market revenue. The generators will only receive this side payment when it is a positive value. Typically, a linear version of the UC is obtained as an initial solution for the discrete optimization model, so this process should not imply a significant additional cost in terms of computational effort. Probably, it will be substantially easier to compute than the Lagrangian relaxation. It is relevant to point out that not all linear problems that derive from a UC are adequate to calculate the prices described. An example is useful to gain insight into the effects of prices on the generation mix. The appendix shows formally the relationship between the dual variable and the market price. Specifically, we show that a market with a price equal to dual variable has the same long-term incentives as a global cost minimization problem under the same hypotheses. The appendix shows formally the relationship between the dual variable and the market price. Specifically, we show that a market with a price equal to dual variable has the same long-term incentives as a global cost minimization problem under the same hypotheses. Dispatch and costs for the global solution. For these data, the overall optimum, the results that minimize the total cost of operation, plus the investment, are presented in the table. It should be noted that there is a rationing of 200 megawatts in the first hour. This is the optimal decision considering the willingness to pay defined in the example. In other words, the bidders define what is optimal to ration in an hour. The decision to build more capacity from technology I1 instead of having 200 megawatts of rationing is related to the adequacy topic that we are not covering in this conference. Economic results for the price equal to the variable cost of the marginal unit pricing rule. In cases where the generator is at its maximum capacity, so the marginal cost is not defined, the rule of choosing the price of the next unit is used. The table shows the market results when prices are set at the variable cost of the marginal unit. These results include lateral payments. Comparing tables 3 and 4, the market results imply that the I2 generator is underpaid, receiving $612 while its total operation plus investment costs is $640. These market results mean that investments in technology I2 are less profitable than required. Consequently, market players will tend to build less I2 capacity, which in turn implies that the generation mix will adapt to the economic signals contained in prices. Market results for the price equal to the variable cost of the marginal unit pricing rule and the technology mix adapted to it. The table shows the market results corresponding to the technology mix. The prices corresponding to the new technological combination are the same, but the complementary payments change. I2 technology reduces its installed capacity in response to prices. This allows us to capture higher prices and compensate for the previous underpayment. Both generators receive their full cost, but the total costs in Table 6 are higher than the total cost of the overall solution, Table 3. This means that the generation mix induced by the price equals the variable cost of the marginal unit rule is not optimal and is more expensive for consumers. Market results for the pricing rule proposed in this paper. One of the most relevant changes is the inclusion of the startup cost of the I1 generator in the price of the T5 hour. Since the plant starts at that time and the commitment variable is continuous, the startup costs are included in the marginal cost. This allows for an additional remuneration for plant I2, as the startup cost moves from the side payment to the marginal price, and this is a price signal for the baseload generator, pointing out that an additional investment in technology I2 would also save the startup costs of I1. Besides, the price in T4 is modified to reflect the willingness of generator I1 to avoid shutting down during that hour. Indeed, if there were an additional megawatt of demand at hour T4, the I1 generator could produce 1 megawatt of its stable minimum load, which means committing 2.5 megawatts and thus saving $175 per megawatt hour in avoided startups during the next hour. The total savings of the I1 would be lower, as it would have to spend $60/MWh in variable costs, so it is finally willing to pay $115 per megawatt hour to produce in the T4 hour. The duality gap complicates the mathematical analysis of auctions when they are not convex. All science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.